welcome to Meduhub. I am Neha Gupta from your chemistry faculty, and in today's video we are going to be talking about amines. So till now we have spoken about organic compounds which either contain carbon and hydrogen only, those are hydrocarbons, or the organic compounds which contain oxygen along with carbon and hydrogen. Such compounds are alcohols, phenols, ethers, esters, carboxylic acids, aldehydes and ketones. Now there is another class of organic compounds which contain nitrogen atom in them. So here we are talking about amines, and amines can be considered as derivatives of ammonia in which either one or two or all three hydrogen atoms of ammonia are replaced by an alkyl or an aryl group. So if they are replaced by an alkyl group, it would mean that the amine is aliphatic. So when we are talking about an aliphatic amine, this is the nitrogen atom. It has two hydrogens attached to it and one hydrogen was replaced by an alkyl group R. Now here the nitrogen attached to one alkyl group, that is, it is directly connected to one carbon atom. This means that this is a primary amine or a 1 degree amine. The second category of aliphatic amines is when two hydrogens of ammonia are replaced by alkyl groups. So we have NH, this is replaced by R and R here. Such amines are secondary amines or 2 degree amines. The NH2 group is called the amino group and the NH group is called the imino group. Now, if all three hydrogens of ammonia are replaced by R groups, such an amine is a tertiary amine or a 3 degree amine, and this nitrogen is called the tertiary nitrogen atom. These are aliphatic amines. Now, if instead of the R group we have an aryl group, so we will get a category that would be aromatic amines. Just like aliphatic amines, aromatic amines can also be primary, secondary or tertiary. Now, we have ammonia attached to two hydrogen atoms and the third valency is satisfied by a benzene ring here. This is the simplest of the aryl amines and this is called aniline. So aniline is a 1 degree amine. So we can say that when to an amino group an aryl group is attached, this is a 1 degree aromatic amine. Now, to NH, if there are two aryl groups attached, or if to NH there is one aryl group attached and the third valency is satisfied by an R group, both of these classify as aromatic amines, and since there are two groups attached, this means they are secondary aromatic amines. The presence of an arene here classify these as aromatic amines. So these are secondary aromatic amines. Now, if all three hydrogens are replaced just like in aliphatic amines here, so we will have a nitrogen attached to three aryl groups, or we can have a nitrogen attached to two aryl groups and an R group here, or we can have a nitrogen attached to an aryl group and two R groups. All three of these are aromatic amines, and because all three valencies are now not occupied by hydrogen but by different groups, all these three are tertiary aromatic amines or 3 degree aromatic amines. So this is the classification of amines. It can be aliphatic or aromatic and it can be primary, secondary or tertiary. Now coming to the structure of amines. Look at ammonia first. This is the structure of ammonia. It contains, nitrogen contains a lone pair of electrons here. So this is a pyramidal structure. Just like ammonia, amines also have a pyramidal structure. So we have nitrogen, let's say an alkyl group like CH3, H and H here, and a lone pair of electrons on nitrogen. This nitrogen is sp3 hybridized. And the geometry would be tetrahedral. because you can say it is a type of A being the central atom, B3, E being the lone pair, AB3E type of molecule. So it is a tetrahedral geometry, but the shape would be pyramidal. That is because the fourth position is occupied by a lone pair of electrons. So this is a 1 degree amine. Similarly, if we have a 2 degree amine, that is also pyramidal with a tetrahedral geometry, or we can have a 3 degree amine. Here all 3 positions are occupied by a methyl group. This is also pyramidal with a tetrahedral geometry. Now, because of the presence of a lone pair, the angle here is always less than 109.28. Why is it so? Because of repulsions between the bond pair and lone pair. So, in the case of amines, the bond angle will depend on the type of R group attached. For example, in this case here, the bond angle is 108 degrees. So, it will vary for every amine depending on the type of R group. This is the structure of amines. Systematically moving on, now let us see how amines are named. So, we will talk about the nomenclature of amines. Alright, so the first thing is nomenclature of aliphatic amines. We have two systems, common as well as IUPAC. We will see the common system of nomenclature first. Under the common system, amines are named as alkyl derivatives. Alright, so the common name would be alkyl amine. You look at the simplest example here. We have a nitrogen atom attached to a methyl group and 2 hydrogens are there. So this is a primary amine. There is only one methyl group. This will be called methyl amine. Here in the second example, to this nitrogen, 2 CH3 groups are attached. This is a secondary amine. Now since 2 methyl groups are there, it will be dimethyl amine. And in the third example here, 3 methyl groups are there. This is a tertiary amine. Under the common system, it will be trimethyl amine. Let's look at this example here. It is slightly more complicated. Look at the 3 groups attached to this nitrogen here. This is an ethyl group. This is also an ethyl group. And this one is an isopropyl group. So now we have 3 groups, 2 ethyls and 1 isopropyl. Going alphabetically, ethyl comes first. So we have diethyl. One word, diethyl isopropyl amine. So this will be the common name of this particular molecule here. This is a tertiary amine. There's another way. Look here, now there are 2 NH2 groups attached at the terminal carbons. And these 2 NH2 groups have CH2 groups in between. So if we count them, there are 6 methylene groups and there are 2 NH2 groups at the terminal ends. So this will be called hexamethylene. Prefix hexa for methylene because there are 6 methylene groups, and di for amine because there are 2 amino groups at the ends. This is the common nomenclature. Let's see how we name amines according to the IUPAC system. According to the IUPAC system, amines are named as the alkane derivatives. So you drop the E of the alkane and the name would be alkane amine. Here again the simplest example, a methyl group attached to NH2. This is a derivative of methane. So we will write methane without the E and amine. This is one word, methane amine. Okay. Here we have 3 carbons. This is a propane. To the first carbon of the propane, an NH2 group is attached. So this will be propane without E. We need to specify where the NH2 group is because it can be attached here as well, right? So here it's on the first carbon, so propane 1 amine. In this example, now what do you do when it's a secondary amine? These 2 were primary amines. If you have a secondary amine, you look at the length of the carbon chain. This has 2 carbons here. This is a methyl group. This is a methyl group. So for naming secondary amines, you will take this part with the longer carbon chain as the parent amine. So this will be an ethane amine. Now to an ethane amine, the nitrogen is attached to a methyl group. So N will be used as a locant to denote the position of the methyl group. So this will be named as N-methyl, and the parent amine is ethane amine. Ethane without the E and amine. So the longest carbon chain is taken as the parent amine, and the substituent attached to it is determined by the locant N. So you write N instead of 1, 2, 3. Here the substituent is on the nitrogen atom. So capital N. Let's look at this example here. Now this is a tertiary amine. This is an ethyl group. This is also an ethyl group. This one is a butyl group. So 4 carbons. This will be considered as the parent amine. So this is a butane amine. Now butane amine has 2 ethyl groups attached to this nitrogen. So since there are 2 ethyl groups, we will write N twice, N comma N, diethyl. This is butane amine. Alright. So these were aliphatic. So this is how you name, according to the IUPAC system, the aliphatic amines. Coming to the aromatic amine, we have already spoken about the simplest of the aromatic amine, where to a benzene ring NH2 group is attached. So this is called aniline. Aniline is the accepted common as well as the IUPAC name, but just like alkane amines, we can name them as arene amines. So you take the name of the arene to which the NH2 group is attached, drop the E. So this will be called benzene, B-E-N-Z-E-N amine. Benzene amine as one word. Or this is also called aminobenzene. So this is the simplest of the aromatic amine. Now coming to this one, here to the benzene ring, an NH2 group is attached here. We have a substituent at the second carbon, that is a methyl group. So one way is to write 2-methyl aniline. This is also called toluidine. So it is orthotoluidine. This is the common name for a benzene ring to which an NH2 group and a CH3 group is attached. If this CH3 group is at the para position, this would be called para-toluidine. If the CH3 group is at the meta position, it will be called meta-toluidine. Alright. So now look at this example here. If you look at the parent aryl group, this is a naphthalene molecule. This is naphthalene, and to naphthalene an NH2 group is attached. So this will be called naphthalene, dropping the E, amine. All these were primary amines. Now coming here, this is a tertiary amine. Just like in aliphatic amines, this is considered as the parent amine, and to this nitrogen 2 methyl groups are attached. So this would be N-N dimethyl aniline. N-N dimethyl because 2 methyl groups are at the nitrogen, and this is the parent amine, which is aniline. Alright. This example is a little tricky. If you look at the substituent that is there on this carbon, it is a CHO group or an aldehyde group. Now you need to remember the order of preferences. So an aldehyde group is always given preference over NH2 group. So this will be the parent group here. The parent compound here would be a benzaldehyde to which an amino group is attached. So this is carbon 1, 2 and 3. So this will be 3-amino benzaldehyde. So this is it for the nomenclature. Okay, moving on to the physical properties of amines. Physical properties. The lower amines containing 1 or 2 carbon are gases with a fishy smell. Amines containing 3 carbons or more are oily liquids, and still higher number of carbons are solids. Aromatic amines are also colorless, but they develop a slight color upon oxidation when we store them for too long. So now coming to the solubility of amines. So amines are obviously soluble in all organic solvents. When you come to water, lower amines are soluble in water. That is because they are able to form hydrogen bonds with water. So lower amines are soluble in water. As the molar mass increases, or as the length of the hydrophobic part in an amine increases, the solubility obviously decreases. So when you move on to higher amines, the solubility gradually decreases, and aromatic amines are not soluble in water. Now moving on to the boiling point. If we talk about 1 degree amines, so we have R, N, H and H. You're talking about the boiling point, so we need to see how the molecules of amines are associated with each other. So there is another molecule here, R, and let's say another one here. So you will see that every nitrogen has 2 hydrogens. So there is extensive hydrogen bonding between the molecules of amines. But if we move on to 2 degree amines, now there is only 1 hydrogen attached to the nitrogen, R, R, and we have this amine here. So there is hydrogen bonding in a 2 degree amine also, but it is less compared to the 1 degree amine. If we move on to tertiary amines, all 3 positions are occupied by R groups. So this would mean there is no hydrogen bonding. So if we talk about isomeric amines, the boiling point of 1 degree would be the highest because there is extensive hydrogen bonding, followed by 2 degree, and the boiling point of tertiary amines will be the least. Alright, now if we compare amines to alcohols, first you need to understand why we are doing so. Because in alcohols, you have an electronegative atom oxygen to which hydrogen is attached. In amines also, we have an electronegative atom nitrogen to which hydrogen is attached. Now, if you talk about the electronegativity of nitrogen in amines and oxygen in alcohols, it's 3, and oxygen in alcohols is 3.5. What does this imply? This implies that alcohols are more polar than amines. Since electronegativity of oxygen is more than that of nitrogen, it means that alcohols can form stronger hydrogen bonds compared to amine. Now, if the hydrogen bonding is stronger, this would mean that alcohols are more soluble in water and their boiling point will be higher than amines of similar molecular masses. Stemming from electronegativity, we can also see that we can compare the acidity of alcohols and amines. So we have an alcohol, when it ionizes, it gives an alkoxide ion Ro minus and a proton. If we write a similar reaction for amines, we would get this ion here where the nitrogen carries the negative charge now and a proton. If we compare these two, we will see that here the negative charge is on oxygen, and in the case of amines the negative charge is on nitrogen. Now because oxygen is more electronegative, it means that it will be able to hold this negative charge much more easily or to a much greater extent compared to nitrogens. This means that since oxygen is able to hold the negative charge to a greater extent compared to nitrogen, alcohols are more acidic than amines. This is it for the comparison between amines and alcohols. Next, we move on to a very important topic, basic character of amines. So a question from basic character of amines has cropped up in NEET exams many a times. So probably not last year, but 4-5 years before that, this question used to come up regularly, and we have a lot of examples you can compare and give the order of basicity. So we need to understand first of all why amines are basic. Basic nature of amines. So there are two reactions which tell us that amines are basic in nature. Now amines have a lone pair on nitrogen atom. So because of this lone pair, they act as Lewis bases because they have an ability to donate this lone pair. Alright, so if we have an amine, it reacts with an acid like HCl, giving us a salt R NH3 plus Cl minus. Okay, if we have an aromatic amine also, this also gives us a salt. So the reaction of amines with acids, where amine reacting with an acid gives us a salt, tells us that amines are basic in nature. Also, amines furnish OH minus ions in water. Since they are giving us hydroxide ions, it means amines are basic in nature. So if we have RNH2 reacting with water, nitrogen has the ability to take away a proton from water. So this would give us again RNH3 plus and OH minus ion here. So these reactions of amines tell us that they are basic in nature. Similar reactions can be written for secondary and tertiary amines. So if we have R2NH reacting with acid like HCl, it will give us R2NH2 plus Cl minus. And if we have a tertiary amine, R3N plus HCl, it will give us R3NH plus Cl minus. So the formation of this salt tells us amines are basic in nature. Alright, sorry for this. Now we need to see, are amines more basic or less basic than ammonia? Because amines are derivatives of ammonia. So if you compare amines to ammonia, let us talk about aliphatic amines first. So we have R group attached to the nitrogen atom. we know that R group has a plus I effect. What happens because of this plus I effect? R donates electron density to nitrogen, which makes the lone pair on nitrogen more available for donation. Now, if the lone pair is more available for donation, the basicity of amines arises because of the lone pair. If it is more available for donation, this would mean that amines are more basic. While in the case of ammonia, only hydrogens are attached to nitrogen, so no such inductive effect is in play here. Hence, we can say that aliphatic amines are more basic than ammonia. If you talk about aromatic amines, we'll take the simplest of the aromatic amine, that is aniline. What is happening here? To nitrogen, an aryl group is attached. Now, aryl group does not have a plus I effect. The lone pair on nitrogen is involved in resonance. That is a plus R effect with this ring. So, we can draw the resonance structures. Get a negative charge here. Now, this negative charge is because of 2 electrons which move here. This moves here. And the next structure can be drawn like this. And so on. So what do you observe in aromatic amines? In aromatic amines, the lone pair is involved in resonance with the ring, and hence it is not that easily available for donation to another molecule. This means that aromatic amines are less basic than ammonia. And obviously less basic than aliphatic amines. Now let us take both of these in detail. So we'll do a comparison of ammonia and aliphatic amines. Now aliphatic amines are classified into 3, 1 degree, 2 degree and 3 degree. It is because of this the discussion about basicity in amines would be slightly more different than what we have discussed about acidity in alcohols or acidity in phenols or carboxylic acids. The difference with amines is that there are 3 categories of amines now. So what happens here? If you have ammonia, this reacts with an acid to give us an ammonium salt. H plus here and Cl minus. If you have a 1 degree amine, this reacts with an acid to give us this salt with 1 R group and 3 hydrogens, plus and minus. If there is a 2 degree amine, now we will have 2 R groups reacting with acid. So this nitrogen has 2 R groups. This will be the salt. And if there is a tertiary amine, there are 3 R groups. R, 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 H and Cl minus. Now what is the difference between these? Here there is 1 R group which is donating electron density in this direction because of the plus I effect. So the inductive effect in this reaction here in a primary amine is due to 1 R group. In a secondary amine, there are 2 R groups simultaneously donating their electron density to this nitrogen atom. So there are 2 R groups. The plus I effect is of 2 R groups. In tertiary amines, the plus I effect is from 3 R groups. So we can say that it is almost like 3 times the inductive effect that is there in primary amines. So the plus I is because of 3 R groups. This means that if you talk about primary amines and compare them to secondary and tertiary amines, the lone pair of electron on nitrogen is more available for donation in tertiary amines because 3 R groups simultaneously are pushing their electron density towards nitrogen, making the lone pair the most available for donation. And obviously by comparison, in primary amines only 1 R group is there which is pushing its electron density towards nitrogen, making the lone pair available for donation. So comparing 1, 2 and 3 degree, we'll see that the 3 degree amine has to be and is the most basic. Now we can look here at the salts also formed. Since this is a base, this will be the conjugate acid. We have to talk about the stability of the conjugate acid as well. What happens if the conjugate acid of a base is stable? This would mean that that particular compound is more basic because the product is more stable than the reactant. So let's see how is it that the R groups are increasing the stability of the conjugate acid. Nitrogen has a positive charge. R is donating its electron density in this direction. It is helping in dispersal of the positive charge, hence contributing to the stability of this conjugate acid. In the second case, 2 R groups are donating their electron density to a nitrogen atom which has a positive charge. This means that there is more dispersal of the positive charge in this molecule here. So this conjugate acid is even more stabilized. And now if we talk about this one here, 3 R groups are simultaneously donating their electron density to a nitrogen atom which has a positive charge. So this means that the positive charge is further getting dispersed. Hence, looking at the stability of the conjugate acid also, we can say that a tertiary amine is more basic compared to a secondary or a primary amine. So this order is observed in the gaseous state. So if we have primary, secondary and tertiary amines at the gaseous state, the order of basicity is 3 degrees greater than 2 degrees and 1 degree, and obviously this is greater than ammonia, which we have already discussed. Alright, so this is the simple order that is followed in gaseous state. Now if we talk about aqueous phase, things become slightly complicated because you know that amines can form hydrogen bonds. Alright, so you're talking about aqueous phase now. In aqueous phase, one effect that is into play is inductive effect, like we have already discussed. Now, since there are water molecules also present, there's another effect that is called the solvation effect. How will solvation effect affect the basicity of primary, secondary and tertiary amines? If the amine is more solvated and if the conjugate acid that is formed is also more solvated, this would mean that the conjugate acid of this amine is more stable if it is highly solvated, and that would increase its basicity. And how does solvation take place? Solvation will take place with the water molecules because of hydrogen bonding. And the third effect that is in play here is the steric hindrance. The steric hindrance to solvation. The steric hindrance to solvation due to the presence of alkyl groups R. Now, the subtle interplay of these three effects will determine which amine is the most basic out of primary, secondary and tertiary. So, if we take the example of methylamines, we have the simplest of primary methylamine. Then we have a secondary methylamine with 2 methyl groups, and we have a tertiary methylamine with 3 methyl groups. We have already spoken about the inductive effect of the methyl group. Now, if we take into consideration the solvation effect, we have water molecules around these amines. Alright, so because of this oxygen here and the hydrogen present on amine, hydrogen bonding will take place here. This amine has 2 hydrogens for hydrogen bonding with water. Alright, so the salt formed here will be more solvated because the number of hydrogens present is more solvated compared to 2 and 3 degree, because with 2 degrees we have just 1 hydrogen here. Okay, so we have this will form hydrogen bond here, and here there is no hydrogen. When we talk about their conjugate acids, each one will have another hydrogen and a positive charge here. So now look at the conjugate acids. If we compare the conjugate acids, again 1 degree will be the most solvated, 2 degree will be slightly less solvated compared to 1 degree, and 3 degree will be the least solvated because only 1 hydrogen is there now attached to nitrogen atom. See, if we compare the solvation effect, we will see that this is most solvated and this is the least solvated. So because of inductive effect and solvation effect occurring simultaneously, you will see that if we see the order here, 3 degree, 2 degree, 1 degree, the tertiary amine becomes less basic than both secondary and primary amines. So if we talk about methyl amines, the order is 2 degree, 1 degree, then 3 degree, and obviously ammonia here. So this is the order followed for basicity of methyl amines. The tertiary methyl amine, because of solvation effect, becomes least basic and it moves here. And the order now is 2, 1, 3. And ammonia still remains the least basic. So this is the order for methyl amines. Now if you talk about ethyl amines, right, ethyl amines, along with the inductive and the solvation effect, in ethyl amines, steric hindrance will also take place because now the ethyl group is larger compared to the methyl group. So this ethyl group will prevent solvation from happening because of steric inhibition. So what is happening? This nitrogen has bulky groups attached to it and then there are water molecules around. Because of these bulky groups, solvation will also slightly decrease. What happens because of the interplay of now these 3 effects in ethyl amines? The tertiary one becomes less basic than the secondary one but remains more basic than the primary one. So the order for ethyl amines is this. Okay, so this is for methyl amines, this is for ethyl amines in aqueous phase. This has been asked many times in the NEET examination. So you need to, it's easy to remember if you look at the order in the gaseous phase. In methyl amines, the tertiary one becomes less basic than both of these and moves here. And in ethyl amines, the tertiary amine becomes less basic than 2 degree but stays more basic than 1 degree and moves here. So this is the order for aqueous phase. In the gaseous phase, it is very straightforward. Only inductive effect is into play and tertiary amines are the most basic and secondary followed by secondary amines, then primary amines. But in aqueous phase, this is the order that is followed. Alright, so this is about alkene amines versus ammonia. Now we'll compare aryl amines with ammonia. So we've already spoken about the lone pair of electrons in aniline being in resonance with the ring, and because of that it is less available for donation. So aryl amines are more basic than ammonia. We can also look at the stability of the conjugate acid in this case. So this is ammonia. We have already drawn the structures. I'll just draw them again. This will move here negative charge on this carbon. Now the negative charge will come on this carbon here. If you look at the conjugate acid of this, of aniline, it is the anilium ion here. This is the anilium ion. If the conjugate acid of a base is more stable, it would mean that the given compound is more basic in nature. But for anilium ion, you see that you can only draw two resonating structures. The second one is this. So only two resonating structures contribute to the stability of anilium ion, whereas 1, 2, 3, 4 and the fifth one, 5 resonating structures contribute to the stability of aniline. This implies that aniline is more stable than anilium ion, which means that aniline would be a weak base. Okay, if we have substituents on aniline, so if we have an electron donating group attached to aniline like OCH3 or methyl group, these groups are pushing their electron density towards the nitrogen. So what happens because of the electron donating effect of such groups, the lone pair on nitrogen now is more available for donation, because these groups are opposing the resonance of the lone pair of electrons with the ring. The lone pairs on nitrogen want to come into resonance with the ring, so they are moving downwards towards the ring. Now if there's such a group, electron donating group present on the ring, it is pushing the electrons in the exact opposite direction. Because of that, electron donating groups increase the basicity of aniline. Increase the basicity of aryl amines or substituted anilines. If you have electron withdrawing groups like NO2, COOH, etc. attached, so what will electron withdrawing groups do? The lone pair of electron on nitrogen is coming into resonance with the ring. Such groups, if they are attached to the benzene ring, will further pull away those electrons towards themselves. So this would imply that the lone pair that was already into resonance with the ring is further being pulled away from nitrogen. Because of that, there is a decrease in basicity. So if you compare aniline with para-nitroaniline and para-methoxyaniline, this will be the most basic. Then will come aniline, and this is now decreasing the basicity, so it will be the least basic. So this will be the order followed. If we move into more detail, we can say that the presence of substituents will impact the basicity based on their position also, and if they are able to come into resonance with the ring. But all these discussions are slightly of a higher level, and for your NEET preparation point of view, it suffices to know that the presence of an electron donating group increases the acidity and the presence of an electron withdrawing group decreases the basicity, sorry. Alright, so this is the order. Now another interesting example is comparing benzyl amine. Benzyl amine with ammonia, aliphatic amine and aromatic amine. So if we draw structure of benzylamine. This is benzylamine here. This is an aromatic amine, but the aromatic ring is not directly attached to aniline or to the amino group here. Nitrogen has lone pairs of electrons, but these lone pairs, this lone pair cannot come into resonance with the ring because it is not in conjugation with the ring. So at best, it is like a phenyl substituted aliphatic amine. Now CH2 group would want to donate its electron density towards nitrogen because it is attached to an electronegative atom. Alright, so it will have a sort of a plus I effect, but that will be somewhat lowered because of the tendency of the benzene ring and the sp2 hybridized carbon here, which is more electronegative and would want to pull the electron density towards itself. This means that if you compare it with ammonia, benzylamine will be slightly less basic than ammonia. Sorry, slightly more basic than ammonia. More basic than ammonia because it is attached to a CH3 group, which would have a slight plus I effect, though it will be less than that of a methyl group. So it will be slightly more basic than ammonia because in ammonia there is no plus I effect whatsoever. But if we compare it to aliphatic amines like RNH2 or a methylamine, methyl group will have a stronger plus I effect. The lone pair would be more available for donation. So benzylamine would be less basic than aliphatic amines. But comparing to aromatic amines, in aromatic amines, the lone pair is in resonance with the benzene ring. It is not available, not that easily available for donation rather. And here, it is not in resonance with the benzene ring. So benzylamine would be more basic than aromatic amines. Alright, so this is it about benzylamines. Now there is another phenomena known as steric inhibition or steric inhibition of resonance. Steric inhibition of resonance. Steric inhibition of resonance also decides the basicity order for aromatic amines. So when will this come into play? So for that we need to first remember that resonance only takes place if the structure of the compound is planar or nearly planar. Now any group attached to the ring which distorts the planarity of the compound will stop resonance from taking place. There will be steric inhibition of resonance. So the resonance will not take place if the planarity of the compound is disturbed. If we talk about N-alkyl amines, N-alkyl aromatic amines, for example this one, CH3 group here on this nitrogen, and compare it to ammonia. Because of the presence of a CH3 group here, this molecule will be no longer planar and hence resonance would be decreased. The extent to which the lone pair can come into resonance with the benzene ring decreases. If the lone pair is not coming into resonance with the benzene ring, this would mean that in N-alkyl aromatic amines, the lone pair is more available for donation compared to aniline. So this would mean that N-alkyl aromatic amines are more basic than aniline. And if in the same example you increase the size of this group, so if we have an N-ethyl aniline, ethyl group is even larger than the methyl group. So there will be more steric inhibition of resonance. This would mean that here the lone pair is even more available for donation, and this will be more basic than N-methylaniline. If the size of the R group or the number of the R group increases, so larger the number of the groups attached to the nitrogen, or if the group attached is getting bigger, it would mean that resonance is further and further inhibited, which further increases the basicity. So to summarize, N-alkyl aromatic amines are more basic than ammonia, and if the size of the alkyl group increases, the basicity also increases. If the number of the alkyl groups increases, the basicity further increases. Alright, so after this is it for the basicity of amines. I'll just take one small example which came in NEET a few years back. So we have these compounds. We have aniline, we have acetanilide, we have a benzyl amine, and para-nitroaniline. Out of these, which one would you say is the most basic? So in aniline, lone pair of electrons is into resonance with the ring. If an NO2 group is present, it is pulling away the electron density, making the lone pair come more into resonance with the ring and less available for donation. Here what is happening, the lone pair is into resonance with the ring. Along with it, this lone pair is also into resonance with the carbonyl carbon here. So in acetanilide, you can say that because of the presence of a carbonyl carbon here, this lone pair is into resonance here as well. Okay, so the lone pair is into resonance with this side as well as this side. So this means it is again not available for donation. So out of these four, in this case, the lone pair is the most easily available for donation, and this one, the benzyl amine, is the most basic. So this concludes our discussion about basicity of amines. Next is preparation of amines. So there are 6 methods for preparation of amines. The first one is reduction of nitro compounds. Preparation of amines. First method is reduction of nitro compounds. So if we have an aliphatic nitro compound like CH3NO2, aliphatic nitro compounds can either be reduced by catalytic hydrogenation. Catalytic hydrogenation would mean we have hydrogen in the presence of nickel, platinum or palladium catalyst, or we can have tin in HCl, or we can have lithium aluminium hydride as the reducing agent. Using any of these reducing agent, an aliphatic nitro compound, that is a nitroalkane, can be reduced to a 1-degree amine. So we have CH3NH2, which will give us CH3NH2, which is a methylamine. If we have we will get CH3, CH2, NH2 and ethylamine, and so on. Now, if we have aromatic nitro compounds like aniline also get reduced to 1-degree aromatic amines. So reducing agents used here are hydrogen gas with nickel, palladium, platinum, again catalytic hydrogenation, or we can use metal in HCl. So we can use tin, iron or zinc in HCl, or we can use, instead of HCl, we can also use acetic acid. So here we have nitrobenzene. This with tin and HCl will give us aniline. So nitro group here was reduced to NH2 group here. If we have an aldehyde group also attached, so if we have, let's say, meta-nitrobenzaldehyde, in such a case, if we use catalytic hydrogenation, what will happen? The benzaldehyde, the aldehyde group here will also get reduced. So to prevent that or to do selective reduction, such a compound can be reduced by using SnCl2 in HCl. That will selectively just reduce the nitro group, and we will get this as the product. So this is reduction of nitro compounds. Now the second method is ammonolysis of alkyl halides, or the Hofmann's method. Ammonolysis of alkyl halides is the only method of preparation that you will study out of the 6, which gives us 2 degree as well as 3 degree amines along with 1 degree amines. The rest of the methods that we are going to do will only give us 1 degree amines or primary amines. Ammonolysis of alkyl halides gives us a mixture of 1 degree, 2 degree, 3 degree amines as well as a quaternary ammonium salt. So for ammonolysis, we can either use an alkyl halide or a benzyl halide. So what happens here? Of alkyl halide. So we have an alkyl halide Rx. This reacts with ammonia. So what happens here? The X or the halide here gets replaced by an NH2 group. So this is like a nucleophilic substitution. And the cleavage of the Rx bond by ammonia is called ammonolysis. This here gets cleaved by ammonia, which is called ammonolysis. So if we have an alkyl halide reacting with ammonia, first it will give us RNH2, which is a 1 degree amine. On further reaction with the alkyl halide, now we will get a 2 degree amine. This 2 degree amine can further react with alkyl halide if it is present in excess to give us a 3 degree amine. And this can again react with another molecule of alkyl halide to give us a quaternary ammonium salt. This one here with nitrogen attached to 4 R groups. So this is the sequence of reaction for ammonolysis. In the first step, ammonia reacts with an alkyl halide to give us a primary amine, and then this primary amine can react with more alkyl halide to finally give us a 4 degree quaternary ammonium salt. So this is a nucleophilic substitution reaction. Let's see how it happens. We have CH3Cl reacting with ammonia. So in ammonia, nitrogen has a lone pair of electrons. This carbon here is electrophilic. Why? Because it is attached to chlorine, which is an electronegative atom, so it has a slight positive charge. This lone pair will, nitrogen with the lone pair will attack on this carbon, and this will leave, giving us CH3, NH3 plus, Cl minus, an ammonium salt here, a methyl ammonium chloride. Now this methyl ammonium chloride, if reacted upon with a base, in this case the base is ammonia, what will happen? This base will take away the proton, one extra proton from this nitrogen, and we will get the primary amine, plus we will get BH. Alright, so the extra hydrogen on this nitrogen was taken away by the base. In this case, the base can be either ammonia because ammonia is already present, or we can use a base like NaOH. So the base will take away a proton and we will get a primary amine. In the second step, now we have a primary amine and we have more alkyl halide. So we have more of CH3Cl. Again, the nitrogen has a lone pair. This can also act as a base. It will attack this carbon and we will get CH3, another CH3 to this, NH2 plus and Cl minus. So we again have this salt here, which on treatment with a base can give us the secondary amine, which would be NH, CH3, CH3. So the base took away a proton from here to give us a secondary amine. In the third step, we have a secondary amine, CH3, NH, CH3. Nitrogen has a lone pair. This can again attack another molecule of the alkyl halide CH3Cl to give us a salt. Now 3 CH3 groups or 3 methyl groups will be attached to nitrogen plus Cl minus. This salt on reaction with the base. Now the base can be this as well as this. Because all amines are basic in nature, so initially we just had ammonia. Now that we have 1 degree amine and 2 degree amine, they also act as bases because the nitrogen has a lone pair of electrons. So that or any other base that is present in the mixture can take away this proton, giving us a tertiary amine. So this tertiary amine now can further react with another molecule of alkyl halide. CH3, 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 this is a tertiary amine. It has lone pairs. So this will attack this carbon and now we will get a nitrogen which is attached to 4 methyl groups. That is a quaternary salt. Now this quaternary salt has no more protons that can be taken away by a base. So this will be the final product. So we get a mixture of 1 degree, 2 degree, 3 degree and 4 degree ammonium salts here. Alright. So this is the entire process of ammonolysis. Now benzyl halides can also undergo ammonolysis. So if we have benzyl halide, this can react with ammonia to first give us a primary amine CH2. This attacks this carbon, Cl leaves, so we will have NH2. Because in the presence of a base, a proton would be abstracted. So this is the primary amine that we get. If let's say this reacts with another molecule of, it's reacting with another alkyl halide. Now we have CH3Cl in the mixture. What will happen now? This can further react. Its lone pair will attack this carbon. This will leave, giving us NHCH3. So this will be a 2 degree amine. If this reacts with another molecule of CH3Cl, we will get a nitrogen attached to 2 methyl groups. So what is happening in the sequence of reactions? We are starting with benzyl chloride and ammonia. If the product that we get, that is a primary amine, reacts with 2 moles of CH3Cl, this is the final product that we are getting here. So this is a tertiary amine. Alright. Now this method is suitable for alkyl halides where the alkyl group is 1 degree or 2 degree. So it gives reasonable or suitable products, the products that we desire. what happens when this R group is a tertiary group? So let's say we have tert butyl chloride. Tert butyl chloride. In tert butyl chloride, what happens? This carbon is a tertiary carbon. It is attached to 3 other methyl groups. Okay, I have written this one as CH2 and H. You'll see why. If this is reacting with ammonia. Now, for ammonia, the lone pair on nitrogen to attack this carbon, there would be steric hindrance because this carbon is surrounded by 3 methyl groups. Alright, so because of that, this base here would prefer to just take away a proton here. Okay, so this ammonia as the base will abstract a proton from this carbon. And why is this proton acidic? Because it is eventually attached to a chlorine atom which is electronegative. So this chlorine is pulling away electron density which facilitates the release of this proton. Since ammonia as a base, it will abstract this proton here. So because of this, what will happen? Ammonia took away the proton and the product that we get would be an alkene. So instead of getting alkene, instead of getting a primary amine, if we have a 3-degree alkyl halide, we will get an alkene as the product. So a monolysis is a method that is more suitable for alkyl halides which have 1-degree or 2-degree alkyl groups. The third method is reduction of alkyl cyanides. Reduction of alkyl cyanides. So if we have CH3, CH2, this carbon and this nitrogen can be reduced. By reduction we mean addition of hydrogen. So the reagents used are lithium aluminum hydride, obviously, catalytic hydrogenation, that would mean hydrogen in nickel, palladium, platinum, or we can also use amalgamated sodium, that is sodium and mercury with ethanol, C2H5OH. So using any of these, an alkyl cyanide or even a benzyl cyanide can be reduced. So we are using sodium in this and C2H5OH in ethanol, sodium in ethanol. This carbon and this nitrogen will get reduced to a primary amine. So reduction of alkyl cyanides to primary amines. This is the amine that we get upon reduction. If we have a benzyl cyanide, this can also be reduced to give us CH2, CH2, NH2. That is an aryl substituted aliphatic primary amine. Here. Now this method can be used as a step-up reaction also. How is that possible? So if you have an alkyl halide, let's say containing 2 carbons, using this method we can convert it into a primary amine containing 3 carbons. How will that happen? So we have CH3, CH2Cl. First, we need to increase the number of carbon atoms in this alkyl halides. For that, we will make it react with KCN in ethanol. So the chlorine will get substituted by the CN group here. We will get CH3, CH2, CN. Now this is an alkyl halide. This is an alkyl cyanide. So this alkyl cyanide now can be reduced using any of the reagents we discussed to give us CH3CH2 CH2NH2. This primary amine now has 3 carbons and the starting alkyl halide had 2 carbons. So this is a step up reaction. After reduction of alkyl cyanides, the next method is reduction of amides. So amides give us 1 degree amine. So reduction of amides gives us primary amines again. The reagents used are either lithium aluminium hydride or we can again do catalytic hydrogenation. So if we have an amide like this one, using lithium aluminium hydride, we can reduce it to a primary amine. So you need to note that we are starting with an amide which has 2 carbons and we are getting an amine which has 2 carbons. So this method will be different from the Hofmann bromide degradation that we'll do. This is the 6th method. So you need to make sure that you're not confused. Here we are reducing an amide. Alright, this method is just reduction of amide. So we get an amine which contains the same number of carbon atoms as the starting amide. This is reduction. Coming to the next reaction, we have Gabriel's phthalimide synthesis. In Gabriel's phthalimide synthesis, we start with phthalimide. Okay, so phthalimide is this. Phthalimide, upon reacting with a base like KOH, first gives us a potassium salt of phthalimide, which on reaction with an alkyl halide gives us the N-alkyl phthalimide. So to this nitrogen to which a hydrogen was attached, now we have an R group. N-alkyl phthalimide, upon basic hydrolysis in the presence of a base gives us a primary amine and phthalic acid eventually. So we'll see how this moves. So Gabriel phthalimide synthesis starts with phthalimide here. So we have phthalimide. This synthesis is used for 1 degree amines, 1 degree aliphatic amines. First, it will react with KOH to give us a potassium salt here. Potassium. This potassium salt, upon reacting with an alkyl halide like RX, this R will get attached to this nitrogen here and the halide will leave. So what is it here? This is phthalimide, and to the nitrogen atom an alkyl group is attached. So N-alkyl phthalimide. N-alkyl phthalimide here. Now to this N-alkyl phthalimide, if you perform basic hydrolysis, so if we have NaOH and water, what will we get? We will get phthalic acid. And the amine here. So this synthesis is only for aliphatic amines. Why? Because instead of an alkyl halide, if we try to use an aromatic halide, so in an aromatic halide, the carbon halide bond is not easy to break because of the partial double bond character here and the sp2 hybridized nature of this carbon. So this bond is difficult to cleave. Hence, it cannot be cleaved by this potassium salt to give us the N-alkyl phthalimide, and hence this synthesis is only used for aliphatic primary amines and not for aromatic. The next reaction is Hofmann-bromide degradation, and this is a very, very important reaction. Again, like we discussed earlier, you have to start with an amide. Now, an amide in the presence of bromine or chlorine and a base like NaOH or KOH gives us a primary amine which contains one carbon less than the amide that we started with. So, sixth Hofmann bromamide degradation. So you have an amide like RCONH2. This, when reacting with Br2 and NaOH, gives us a primary amine which contains one carbon less here. Okay, so we'll have RNH2, we'll have NABR plus Na2CO3 and water. So the product is a primary amine. It is very important to remember, with one carbon less. Here, if we have benzamide also, a benzamide can also react with Br2 and NaOH to give us aniline. So aniline here is a primary amine which contains one carbon less than the starting amide. So this is the Hofmann-bromide degradation reaction, which has come many a times in the exam before, and the trick is to just remember that in the presence of Br2 or Cl2 in base like NaOH or KOH, which is also sometimes written as NaOBr, you will get an amine, a primary amine with one carbon less. Alright, moving on after preparation, now let us see what are the chemical reactions of amines. Chemical reactions. So the first chemical reactions is basicity, which we have already covered. So amines are basic in nature. मैं इसको थोड़ा सा repeat कर देती हूँ. Let's say we have methylamine. Here it will react with an acid HCl. Because it has a lone pair, it will get protonated and we will get a salt. CH3NH3 plus HCl minus. This is a 1 degree amine. Same reaction is given by 2 degree as well as 3 degree amines as well as aryl amine. So if we have aniline, aniline will react with an acid to give the anilium salt. This lone pair or nitrogen makes it a Lewis base. It will get protonated और जो हमें salt मिलेगा, that will be this NH3 plus Cl minus. This salt that is formed here is soluble and can be regenerated to an amine in a basic solution. So अगर CH3NH3 Cl इस salt को NaOH base में dissolve किया, we will get the primary amine back, CH3NH2 plus OH minus will abstract the proton from here. So we will get water, H2O and Cl minus. So you can regenerate the amine which had formed a salt with acid using a base. So this is basicity of amines. Now the second reaction is alkylation of amines. For this, go back to ammonolysis of amines which we started. Because ammonia is a base, it will cleave the bond between an alkyl halide and form a primary amine. Now that primary amine that was formed acted as a base for further reaction, right? So this chemical property here is just a continuation of what we did in ammonolysis, alkylation of amines. So all amines, what is very important to remember here is all amines, aliphatic or aromatic, undergo alkylation. Alkylation, that is a reaction with an alkyl halide. So if we have a methylamine, CH3CH2 NH2, a 1 degree methylamine, this will react with an alkyl halide, say methyl chloride, and form a salt. So what will happen, this lone pair here will attack this carbon because it is slightly electrophilic. This chlorine will leave and we will get CH3CH2 NH CH3CH2, which is a 2 degree amine. So a primary amine gives us a secondary amine. What is happening here, if we write the mechanism, this attacks on this carbon, chlorine leaves and we get a salt. The salt can be written like this. NH2, this again attached to CH2, CH3, positive charge here. This, in the presence of a base, will lead to the abstraction of proton from this salt here and give us the 2 degree amine. Alright, so this is the mechanism of the reaction. Similarly, if we have a 2 degree amine, CH2NH, CH2CH3. So this is a diethylamine. This will react with CH3CH2Cl, an alkyl halide, to give us a tertiary amine. So to this, 3 ethyl groups would be attached. And if we have a tertiary amine to start with, this was 2 degree. On reaction with an alkyl halide, it gave us a 3 degree amine. So it was alkylated to give a tertiary amine. Now if we have a 3 degree amine to start with, this now is going to react with a molecule of alkyl halide and give us a quaternary ammonium salt. So what is a quaternary ammonium salt? This nitrogen now will be attached to 4 alkyl groups here. So the ethyl group will be all around this nitrogen, CH2, CH3, CH2, CH3, and nitrogen will have a positive charge. So the reaction of all amines, here we can also take an aryl amine. The simplest of the aryl amine is aniline. So if we have aniline, aniline will react with, say, CH3Cl, an alkyl halide here, to give us N-methyl-aniline. N-methyl-aniline, it can further react with another molecule, giving us N-N-dimethyl-aniline. This nitrogen will now have 2 methyl groups. This now can further react with another molecule, CH3Cl, to give us a quaternary substituted anilium ion. So this nitrogen now will be attached to 3 methyl groups and have a positive charge. Right? So all amines, either aliphatic or aromatic, undergo alkylation with alkyl halides to give us alkyl substituted ammonium halides. Alright? Now the next reaction is acylation and benzoylation. the third reaction. Acylation means that if you have an amine, the NH2 or the NH group of 1 degree or 2 degree amine, here this hydrogen is substituted by an acyl group. So in acylation reactions, the hydrogen attached to the nitrogen is substituted by an acyl group, which is CH3, COCH3. So acylation takes place in the presence of esters, acid anhydrides, or acid chlorides. We can take multiple examples. We have ethane amine here. Okay, this will react with acid chloride CH3COCl in the presence of a base. So here the base that we use is usually pyridine or some base which is more basic than the amine that we are using. What is the reason for that? We'll just see. Here what will happen, one of the hydrogen atoms on this nitrogen will get substituted by an acyl group. So acylation will take place. We will have C2H5 NHCOCH3 plus HCl. So if we have a base present, it will neutralize the HCl and make the reaction move in the forward direction. We can take more examples. If we have a secondary amine, it can react with acid anhydride, in the presence of a base to give us so अब इस नाइट्रोजन पे 1 हाइड्रोजन था, ये हाइड्रोजन एसाइल ग्रुप से रिप्लेस हो जाएगा. So we will have this as the product plus अब HCl नहीं होगा because we have acid anhydride here, we will get acetic acid CH3COOH. So all aliphatic and aromatic 1 degree and 2 degree amines undergo acylation. If we talk about aromatic, we have aniline. Aniline can react with, let's say, as CH3COCl, acid chloride, to give us acid amide. 1 hydrogen will get replaced by the acyl group. This is acid amide. Similar to acylation, benzoylation can also take place. So for that we'll use benzoyl chloride. Starting with an aliphatic amine, let's say CH3NH2, a simple one, reacting with benzoyl chloride. Here what will happen? 1 hydrogen will get replaced by a benzoyl group. So this will give us this is the benzoyl group. 1 hydrogen will get replaced, so we'll have NHCH3. This will be the product here. And if we make aniline react with benzoyl chloride, similar reaction will take place. So this is aniline reacting with benzoyl chloride. Now this is easier to visualize if I have drawn it like this. One of the hydrogen and the Cl moves, they join together to give us this as the product. NH, C double bond O and another benzene ring here. So this is the product of benzylation. Now the third reaction, fourth in the sequence, is carbylamine reaction. Carbylamine reaction is extremely important from NEET point of view. Let's see the fourth one. Carbylamine reaction. So if you talk about aliphatic and aromatic 1 degree amines, this carbylamine test can be used as a test for them. So you can detect the presence of a 1 degree aliphatic or aromatic amine using the carbylamine reaction. 2 degree and 3 degree amines do not give this reaction. So carbylamine reaction is not given by 2 degree, 3 degree amines. Only 1 degree aliphatic as well as aromatic amines give this reaction. So what happens in a carbylamine reaction? We have an amine RNH2. It reacts with chloroform CHCl3 in the presence of a base KOH to give us an isocyanide or a carbylamine. An isocyanide is nitrogen triply bonded to carbon like this and an R group this side. So we have an isocyanide here. So 1 degree amine, look here, reacting with chloroform and KOH gives us isocyanide and KCl and water. What is special about this test is that isocyanides are foul smelling substances. So you can detect the presence of a 1 degree aliphatic or aromatic amine by the smell that comes. If you have a 2 degree or 3 degree amine, this smell will not be there because a carbylamine or an isocyanide will not be formed. Similarly, you can write the reaction for aniline also. Aniline reacting with chloroform and KOH gives us this isocyanide, which is again a foul smelling substance. What you need to remember about carbylamine reaction is the reagent that we use, chloroform in a base. Coming to the next one, the fifth reaction is a very interesting reaction, that is the reaction with nitrous acids. This reaction is also used to detect the presence of 1 degree, 2 degree or 3 degree amines. It is also, we can also call it the test for 1 degree amines, because all 3 categories of amines give different reactions with nitrous acid. Nitrous acid is HNO2. So let's talk about aliphatic amines first. So we have a 1 degree aliphatic amine, like CH3CH2 NH2, ethylamine. Now this ethylamine will react with HNO2 at a low temperature to form an aliphatic diazonium salt. An aliphatic diazonium salt is like this, N2 plus Cl minus. This is called an aliphatic diazonium salt. Now this aliphatic diazonium salt that is formed is very unstable because there is no stability associated with it, no special or extra stability. Alright, and we'll discuss more about diazonium salts when we talk about aromatic diazonium salts in the next video. But this aliphatic diazonium salt is not stable. So this in water gives us CH3, CH2OH and alcohol, and nitrogen is released. Alright. That's HCl. So we get an alcohol from a 1 degree amine. You can say 1 degree amines give us alcohols. What happens with 2 degree amines? 2 degree amines do not form diazonium salts. 2 degree amines form nitrous amines. So if we have a 2 degree amine NHCH3 on reaction with nitrous acids, it will give us nitrous amine, CH3 whole twice N and NO here. This is a nitrosamine, and a 3-degree amine gives us a nitrite salt. So if we have CH3 whole twice N reacting with HNO2 gives a nitrite salt. This would be CH3 whole thrice N plus HNO2 minus a nitrite salt. So what you need to know is that only 1-degree amines form unstable diazonium salts which immediately give us alcohol. So 1-degree amines upon reaction with nitrous acid give us alcohol. This is not given by 2 and 3-degree amines. Hence, the reaction with nitrous acid is used as a test for 1-degree amines. Coming to aromatic amines, similar to aliphatic, a 1-degree aromatic amine also gives us a diazonium salt. So aniline on reaction with HNO2. So this HNO2 is prepared in situ, that is inside the reaction mixture with NaNO2 and HCl. At a low temperature of 0 to 5 degrees gives us an aromatic diazonium salt. N2 plus Cl minus. Now this diazonium salt is more stable compared to the aliphatic one, and it does not give us an alcohol. This is an aromatic diazonium salt. We will discuss more about it later. If we talk about 2-degree and 3-degree aromatic amines, so if we have AR, NH, AR, this again gives us nitrosamines. And in the case of a 3-degree, we will have substitution in the benzene ring. Okay, so we have AR, NR2, a 3-degree aromatic amine. In HNO2, the aromatic ring will have an NO substitution at the para position, and this is the NR2 group here. Alright, so this is how aromatic and aliphatic 1-degree amines differ from the 2 and 3-degree amines. So this was the reaction with nitrous acids. Coming to the next one, it's called the Hinsberg method. Again, this is also a test for 1-degree, 2-degree and 3-degree amines. So 6th one is also very important. Hinsberg method or Hinsberg reaction. Hinsberg reaction can be used as a method to separate the 3 categories of amines or to test for 1-degree, 2-degree and 3-degree amines. What happens in the Hinsberg method? First, the mixture of amines is treated with the Hinsberg reagent. Okay, Hinsberg reagent is benzene sulfonyl chloride. Hinsberg reagent is benzene sulfonyl chloride. The mixture is treated with benzene sulfonyl chloride. Now, and then it is treated with an alkali like KOH. So what is observed is that 1-degree amine is soluble, 2-degree amine is not soluble, and 3-degree does not react. We'll see how. So we have a 1-degree amine CH3 NH2. This reacts with Hinsberg reagent, which is benzene sulfonyl chloride. This one here, okay. A similar reaction to the one we have started earlier with alkyl halides takes place. Chlorine leaves, and we have NHCH3 group here. So this is N-alkylated sulfone amide. N-alkyl sulfone amide. This N-alkyl sulfone amide that is formed with a primary amine is soluble in a base. This is what we spoke about. So if this is dissolved in KOH, it is soluble. So what happens? This is S with double bonded oxygen. This base abstracts this proton from here. All right. This is what we get. So this is soluble in alkali. And this is also resonance stabilized. This particular compound here. So if 1 degree primary amines forms N-alkyl sulfonamides which are soluble in base. How do 2 degree and 3 degree differ? So if we take a 2 degree amine, this one has 2 methyl groups. This secondary amine, when reacting with benzene sulfonyl chloride, here, reacting with benzene sulfonyl chloride, it gives us this is SO2Cl. Let's go back a little. SO2Cl, benzyl sulfonyl chloride. Again, this chlorine leaves. We have nitrogen, H. This hydrogen is no longer there. This gets attached to 2 CH3 groups. So this is NN dialkyl sulfonamide. This NN dialkyl sulfonamide formed from a secondary amine is not soluble in alkali. Not soluble in alkali. Reason being that now there is no hydrogen attached to this here, to this nitrogen atom here, which can be abstracted by a base. So this is insoluble. So 2 degree or secondary amines lead to the formation of a sulfonamide which is not soluble in alkali. With 3 degree amines do not react with Hinsberg reagent. Because 3 degree amines do not have a hydrogen to start with. In all these reactions, the hydrogen was lost from a nitrogen and it bonded with the sulfur atom here. But 3 degree amines do not have a hydrogen to start with. इसलिए ये Hinsberg reagent से react नहीं करते. So if you have a mixture of 3 amines, okay, you add Hinsberg reagent to it and you dissolve that mixture in a base. What will happen if you distill it? जो distillate होगा, distillate 3 degree amine will distill off because it is not reacting at all. Distillate will have this one here, this soluble compound that was formed in the base, and an insoluble product which can be filtered off. The insoluble product will be from the 2 degree amine and the soluble one will be from the 1 degree amine. So that's how you can separate the mixture, or you can also use it as a test to test for 1 degree, 2 degree or 3 degree amines. So nowadays, Hinsberg reagent is being replaced by para-toluene sulfonyl chloride. So there's just a methyl group at the para position. That also gives the same reaction. You just add a methyl group here and para to it here. Alright. Now, coming to the last reaction, it is electrophilic substitution. Electrophilic substitution reactions. If we look at aniline, we will see that the lone pair of electrons of nitrogen comes into resonance with the ring. This leads to a negative charge at both the ortho positions and the para position. if we draw the resonating structures, you will realize that the negative charge comes at both the ortho positions as well as the para position. So this means that NH2 group, that is aniline, is ortho-para directing. And since there is an increase in the electron density at the ortho and para positions, this means aniline is activating for electrophilic substitution. So ortho-para directing as well as activating. Activating means that the reaction will take place faster than it would in benzene. So these three positions become centers of more electron density and an electrophile can attack. Alright. So the main reactions that you have to do in electrophilic substitution is, the first one is halogenation. If you treat aniline with bromine or chlorine water, you will immediately get a white precipitate. This white precipitate would be a trihalo derivative of aniline. So both the ortho positions as well as the para position will be substituted by bromine. This is because aniline, the NH2 group, is ortho-para directing as well as activating. So it activates all three positions and we get a tri-substituted derivative. In case you want only an ortho derivative, what will you do? Or a para derivative. So we have aniline. Let's do the para derivative first. We need to protect this group somehow so that its activating effect is lowered. For that, what do? We treat it with CH3COCl, acid anhydride, acid chloride for acylation. So here what will happen? First we will get acid amide. So this group here, this nitrogen, will become NHCOCH3. This is acid amide, the same acylation reaction that we did. Now look at this group here. Acid amide is ortho-para directing, but it is not as activating as aniline. Why is it so? Because the lone pair on this nitrogen is involved in resonance with the ring as well as with the carbonyl carbon here. So it is not so much available to come into conjugation with the ring because it is supposed to go this side as well as that side. So that is the reason it is not as activating as an NH2 group. So now that we have protected this group and we have made it less activating, we can make it react with bromine. Now we will get the ortho as well as the para derivative. But we will get the para derivative as a major product. So we will get 80% of the para derivative and 20% of the ortho derivative. They can be distilled and separated by fractional distillation. Alright, so we will just concentrate on the para derivative here. We have got this. From this we need to generate the aniline back. So upon hydrolysis, this will give us para-bromo-aniline, NH2 and Br. This as the major product. This is how you get the ortho or the para derivative only. Now if you want the ortho derivative only, what do? For that we need to protect the para position. So for the ortho derivative only, we start with aniline. First, we treat it with oleum to sulfonate the para position. Okay. We get SO3H group here at the para position. Now, para position is occupied. Substitution can only take place at the ortho position. Next step would be to lessen the activating effect of this NH2 group. For that, again, make it react with CH3COCl. This becomes NHCOCH3. This becomes SO3H. Now we make it react with bromine and followed by hydrolysis. a base. So what will we get? We'll get orthobromoaniline. This is how you get the orthoisomer. If we talk about iodination, you can carry out direct iodination of aniline in the presence of sodium carbonate, aqueous sodium carbonate. Now, why is direct iodination of aniline possible? Even though iodine is the least reactive of all the halogens, aniline, the NH2 group in aniline is so activating that it is able to cleave the bond, and direct iodination with iodine is possible. So, for iodination, you use iodine in aqueous Na2CO3. So this is it for halogenation. Next reaction is nitration. So what is interesting about nitration? When you carry out nitration of aniline, along with the ortho and para isomer, you also get the meta isomer. Why is it so? Concentrated HNO3 and H2SO4. So you will get a mixture of ortho, para as well as meta isomer. Meta and para. Now these two are understandable because NH2 group is ortho and para directing. Why do we get the meta isomer? This is also a previous year's NEET question. So what happens? This is an acidic medium. Okay. Since aniline is basic, in the presence of an acidic medium, we get the anilium ion. This is the anilium ion, NH3+. Since there is a positive charge on nitrogen, it will pull away the electron density from here, from this carbon towards this direction, and further from this carbon towards this direction. The electron density is being pulled away. This means that this carbon and this carbon, the ortho and the para positions, become electron deficient because the electron density is being pulled in that direction, which makes the meta position more electron rich compared to the ortho and para position. It is not getting any special addition of electrons. It is just relatively more rich compared to the ortho and para positions because NH3+ group is meta directing now. And the electron density is being pulled away from the ortho and the para position. If you follow these arrows, you will understand. This is the reason that the anilium ion is meta directing. So aniline in an acidic media gives a mixture of ortho, para and meta isomers. So if you need a para derivative only, just like bromination, what do? You protect this group by acylation and then you carry out nitration followed by a hydrolysis. So you will get para nitroaniline. Next is sulfonation. We have aniline. It reacts with oleum to give us this product. So we have NH2 here and SO3H here. What is interesting about this product here is that it is a dipolar compound, or it exists as a Zwitter ion, or you can say it is an ampholyte. What does it mean? It means that in this particular compound, we have a basic group as well as an acidic group together. So we have a basic and an acidic group together in the same compound. So they neutralize each other. That is the reason that this exists as a Zwitter ion, which can be written as a proton from here, from this acidic group goes to the base. So we have NH3+ here and we have SO3- here. So this is the Zwitter ion of this compound. The Zwitter ion accounts for the high dipole moment of this compound because there is separation of positive and negative charge, and it also accounts for the absence of acidic and basic properties. Acidic and basic properties. So this is neither acidic nor basic because both the groups cancel each other out and they become neutral. So this is it for sulfonation. Now, combining the knowledge of all the reactions we did for amines and what we know about alkyl halides and alcohols and carboxylic acids, basically everything that we have done earlier, I have two examples for you which we are going to solve. One is how to ascend a series. That is, when we are starting with an amine with say 1 carbon, how do we move on to an amine which has 2 carbons? The second one is how to descend the series. If we are starting with an amine which has 2 carbons, how do we prepare an amine which has 1 carbon? So we'll do these two examples. This is a step-up sequence. We have methylamine. So this has 1 carbon, alright. The first step would be to react it with HNO2. What will happen when a primary aliphatic amine reacts with HNO2 with nitrous acid? We will get an alcohol. Now keep the aim in mind, we are supposed to increase 1 carbon here. How do we increase a carbon in this methanol? We somehow need to remove this OH group and get another carbon. What do we do for that? First of all, we can make it react with PCl5 or PCl3 or zinc in HCl and ZnCl2 in HCl, and we will get an alkyl halide. So this is a substitution reaction of alkyl halides, right? So this is from that chapter, haloalkanes and haloarenes. Now what do you do? Now we need to increase a carbon. How do you increase a carbon atom in an alkyl halide? You treat it with ethanolic KOH. KCN. You treat it with ethanolic KCN. So CH3CN will be the product here. Now that we have 2 carbons, try to think how do you convert CH3CN to an amine. This can be reduced. How do you reduce it? By catalytic reduction, CH3CN, a cyano group, can be reduced to a primary amine. So this carbon will have CH2, then we'll have NH2. And this is how we prepare an amine which contains 2 carbons, even though we started with an amine which had only 1 carbon. The next example and the last of this video is how to descend the series. The second one is a step down sequence. So we have ethylamine and we have to prepare methylamine from it. First step would be to make it react with HNO2 to get the alcohol, that is removing the nitrogen. Now alcohols can be oxidized in the presence of KMnO4 in acidic media, let's say, to carboxylic acid. So we have CH3COOH now. We get acetic acid. This can be converted into an amide when you heat it with ammonia. So we get CH3CONH2. Now comes into play the important reaction of amines that we did. That was Hofmann-bromamide degradation. Now we have an amide with us which has 2 carbon atoms and we need to degrade it to an amine which has 1 carbon atom. So we will carry out Hofmann-bromamide degradation here. Hofmann-bromamide degradation. We will use Br2 in NaOH and we will get a amine which has only 1 carbon atom. So starting from this ethylamine, we got methylamine. This is how a step-down sequence is carried out. So this is it for today. Thank you so much for watching. I'll see you in the next video.